Hello everyone, my name is Joseph, and in this video I will walk you guys through how to create an image classifier in TensorFlow. We will use one of TensorFlow's provided datasets called CS490, which contains various images from 10 different categories. Instead of a normal IDE, I will use Google Colab, which is a product of Google Research that can be used to write and execute Python code in chunks. It's a very helpful tool for data science and machine learning. So let's get started. These are the libraries we will be using. We will be using TensorFlow for the neural network, NumPy for array manipulation, and Matplotlib for plotting. So step 1 is to load the data. Now as I mentioned, the CS490 dataset is already included with TensorFlow. We simply need to load in the images and labels and store them in training and testing arrays respectively. Now we can take a look at the shape of the data to make sure it looks good. For XTrain, 50,000 is the number of images we have for training. 32 by 32 is the image size, and 3 is the dimension, which in this case represents RGB, or a color image. YTrain contains the labels, so we can see that it's also 50,000, and since these are just labels, it's just a 1 here. And we can see that the only difference for the test arrays is the number of images. We only have 10,000 for testing because we want to use most of the data for training and a small part for testing. Then we can take a look at one of the images in its array representation, which really is just a bunch of numbers representing pixels in the image. By using Matplotlib, we can display the actual image, and as we can see in this case, it looks like it's a truck. Then we print the image label corresponding to this image, and in this case it's giving us a 9. But that is not very informative, so what we do next is to create an array of the corresponding category names so that we can map the labels to its corresponding category and get it as text, which is a little bit more informative. So now we can see that the image is of a truck. Now, since most machine learning algorithms cannot work with categorical data directly, we create 2 new label arrays where we one-hot encode the label numbers to allow the representation of a categorical data to be more expressive. To give a quick explanation, we can take a look at the one-hot encoded array for the truck. And as you can see here, we have an array of zeros where the last value is 1. Well, it's a 1 because truck is at the corresponding index in this array. Now if our image was instead, let's say, an airplane, the 1 would have been at the first index in this array, because airplane is the first category in this array. If that doesn't make sense, or if you want more information on why and how this works, there will be a link in the description. Next, remember how our pixels in the image were values between 0 and 255. Well, we can speed up learning and convergence if we divide all the pixels by its max value of 255 to get a range of pixel values between 0 and 1. This is also known as normalizing. We can now see here in the image arrays that all the pixels are between 0 and 1. Now for the fun part, creating the model. TensorFlow makes it very simple to create models. So by creating something known as a sequential model, we can simply add different layers until we're happy. Now, going into details as to what each of these layers do and how they work is beyond the scope of this video and would just take too long. So I will give a quick description of the purpose of each layer, and if you want to know more details about them and their parameters, there will be a link in the description. Our first layer will be a 2D convolutional layer. This layer creates a filter, also known as a kernel, that is used to detect features such as edges throughout the image. Our next layer is max pooling 2D, which is used to reduce the dimensions of the feature maps. This reduces the number of parameters to learn and the amount of computation performed in the network. Then we repeat those 2 layers. At the end, we flatten the image. Flatten is a function that converts the pooled feature map to a single column that is passed to the fully connected layer. Then we use a dense layer that adds that fully connected layer to the neural network. After that, we use a dropout function, which is used to prevent overfitting. Overfitting is when the model performs well on the training data, but not very well on the unseen or new data. Lastly, we do 2 dense layers, and then we're done. Then we need to compile the model. For this, we use the loss function categorical cross entropy, which is commonly used for multi-class classification. Then we use the Atom optimizer, which is an optimization algorithm for stochastic gradient descent for training deep learning models. And again, for anyone that is interested, I will leave links with more info in the description. Now it's time to train the model by calling fit on the model. So we pass in the training images and the one hot encoded array. We give it a batch size of 256, which refers to the number of samples processed before the model is updated. Then we set epochs to 10, which defines the number of times that the learning algorithm will go through the entire training dataset. Now that the model has completed training, we can evaluate it. As we can see, the accuracy is not super great, but for this example, we used a very simple neural network. If we were to use a more complex neural network with more layers, we would get better results. Now we can plot the model accuracy. And as we can see, the model looks like it was improving nicely here, which is what we expect. If the graph would look a lot different, it would probably mean we did something wrong somewhere. Or if the curve was straight for longer, it means we trained the model for too long and could reduce the number of epochs. Similarly, the loss seems to decrease nicely, which is also to be expected. Now it's time to test the model. I have an image of a cat here, as you can see. The first thing we want to do is resize the image to match the dimensions that the model was trained on. Then we can perform the prediction by calling predict on the cat image. Note that the input is a NumPy array here. Then I have a little algorithm here that will just sort the predictions in order of accuracy. Lastly, by using the text label array we defined earlier, we can print the accuracy like this. So we can see that the model is about 41% sure it's a cat. And yeah, you can see the rest. I hope that was helpful to you guys, and again, there are links with more info in the description. Thank you.